Okay, here is an ALEKS problem dealing with energy. And it says it takes 463 kilojoules per mole to break an oxygen-hydrogen single bond. Calculate the maximum wavelength of light for which an oxygen-hydrogen single bond could be broken by absorbing a single photon. So we're talking about a single bond and the energy it takes to break this bond, and of course we're going to deal with sig figs. Well, let's write down some things that we know here. Okay, the first thing that we know from our lecture is that energy, okay, equals Planck's constant times the frequency. Alright, so that's something that we know. We also know that speed of light is going to equal the wavelength of light times the frequency as well. We know that Planck's constant is going to equal 6.626 times 10 to the minus 34th joule seconds are the units that we're going to use for that. Okay, and then we're also given that we have 463 kilojoules per mole. Now we want to only deal with a single oxygen-hydrogen bond and not a full mole of that, and so that probably should be the first place where we start with this. And so let's just get that down to the energy to break a single bond, not a mole of those bonds. Alright, so we start off with 463 kilojoules per mole. Alright, and what we want to do then is we know that in 1 mole of these bonds there are 6.022 times 10 to the 23rd bonds. Okay, so that gets us down to a single energy per bond, and if I do that math right there, then I find that there are 7.6883 times 10 to the minus 22nd kilojoules. It's not per mole now. It is per a single bond. Okay, so that's going to be per bond. That is the energy that it takes to break one bond in kilojoules. Well, because Planck's constant is in joules, let's just go ahead and get that into joules. And so I know that in 1 kilojoule there are 1,000 joules. And so when I calculate that, then I'm going to get 7.6883 times 10 to the minus 19th joules to break that single bond, okay, per single bond right there. Okay, so I have calculated E right here, but we're trying to get to this particular wavelength, and we're going to have to do that through our frequency right there. So let's just rearrange frequency from this equation. So if I do that, I have frequency is going to equal C divided by the wavelength. The reason why I'm dealing with frequency here is because I'm going to have to tie the energy and the wavelength together, and the only way I can do that is through this equation. And so now I'm going to rewrite this equation, but just substituting in the frequency. And so I have energy equals Planck's constant set of frequency. I'm going to substitute in speed of light divided by the wavelength. And in fact, you can use this equation many different times. Okay, so as I look at that, then I calculated E right here. That's this value over here. And I know Planck's constant, that's giving. I know the speed of light, C equals 3.00 times 10 to the 8th meters per second. Okay, and so I know that energy, I'm just going to rearrange this equation. I'm going to say that lambda just rearranging this equation, equals hc divided by the energy. Okay, so that's what I have right here. I just rearranged this equation because I want to figure out the wavelength. Lambda is the wavelength. And so if I substitute things in right here, then Planck's constant is going to be 6.626 times 10 to the minus 34th joule seconds times the speed of light, which is 3.00 times 10 to the 8th meters per second, divided by this energy, which is 7.6883 times 10 to the minus 19th joules. And so when I solve this problem right here, then I'm going to get that wavelength is going to equal 2.585 times 10 to the minus 7th meters. Okay, so often that is the answer to this, probably not in the right number of sig figs, but often wants for this in nanometers. That's often a more useful help for us. And so let's just hurry and convert that to nanometers. And so I know that in 1 meter there are 10 to the 9th nanometers. And so when I do that math, I know that the answer lambda equals 258.5 nanometers. Okay, so I got to get that in the right sig figs. I look back up here, I see that I have 3 sig figs. And so the answer in nanometers for the wavelength equals 258 nanometers. Okay, so again, to rehash this problem, we know certain things. We know that energy equals h nu, okay, the Planck's constant times the frequency. I also know that the speed of light equals lambda, the wavelength, times the frequency, which is nu. I can use these two equations together to derive this third equation right here. And then another key to solving these types of problems is to know that often we give units of energy in this units of kilojoules per mole. And just know that if we're dealing with a single bond, then we need to get out of kilojoules per mole and get that into kilojoules per single bond. And often, sometimes it'll be the single atom that we have to go to, where in this case we'll divide through by Avogadro's number. So again, these questions are actually really, really doable. It's just kind of understanding the basic algebra, understanding what is asked. Sometimes we'll need to find energy, sometimes we'll need to find frequency, and sometimes we will need to find wavelength. And so using this type of approach to it, you should be able to do these problems.